I wanted to find the area between two curves? So we, of course, know how to find the area under a curve, or between a curve and the x-axis, right? We've talked about that plenty of times. We started by thinking about Riemann sums and those rectangles getting infinitely, infinitely small, and we ended up realizing, oh, we could set up an integral with respect to x, where basically I'm finding the height, if this is my function f of x, I'm finding the height of each rectangle, I'm calling that f of x, and the width of each little rectangle is the change in x. So if I wanted to find, for example, the area enclosed between the x-axis and this curve on an interval from a to b, that would be that integral. Integral from a to b of f of x dx, right? And of course, those rectangles would get infinitely, infinitely small, which would get me the area under this curve. Well, what if I had a second curve that was involved? Let's call that second curve g of x. And what if I wanted just to find the area enclosed between f of x and g of x? Well, stop and think about how you might do that. I bet you came up with what I came up with. I think the way we could do that pretty easily is just to say that's going to be the area under the curve f of x and subtract away the area under the curve g of x. In other words, you're subtracting away all of this area, and that leaves you with the area that you want, which is the area enclosed between f of x and g of x. And of course, this is all with respect to x. So there's the integral of f of x minus g of x dx. That would give me the area enclosed by these two curves, f of x and g of x. Now, if we had a slightly different scenario, let's see if that would work in this situation. Let's say f of x is somewhere up here, blah, 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 right? And let's say that my g of x now is down here, right? And let's say I just wanted to find the area enclosed between those curves on the interval a to b, okay? Is this formula still going to work? Is it still going to be f of x, the area under f of x, minus the area enclosed between g of x and the x-axis? Think about if this equation would find this area. And if you think long enough, I think you'll realize that works for this too. Because of course, this area down here, this signed area is negative. This signed area up here is positive. So I'm taking the area enclosed between f of x and the x-axis, and I'm subtracting the negative area. Two negatives, of course, give us that positive. So this formula here works, this equation works to find the area enclosed by two curves, regardless of where the curves are in space on the xy axis. Isn't that kind of cool? And of course, if I am asking for area, our answer is always going to be positive. Area by definition is positive. Okay, so let's just do a couple of problems now that we've figured out this handy-dandy equation. And let's see how this works. Okay, so here's our first mission. We are going to find the area enclosed by the functions y equals x squared plus 2 and y equals 2x plus 5. I'm going to make a quick sketch. Pictures are incredibly useful here. Remember, you can just plug in an x, get out a y, plug in an x, get out a y. If you're allowed to use your calculator, you can use your calculator. But I know that's a handy-dandy parabola that shifted up to. This is obviously a line, y equals 2x plus 5. So I've got a y-intercept. So it's going to look something like this. And the area I'm interested in is all of this area enclosed by those two curves. So what do you think our first mission is? That's right. We have to find what my interval is. We have to figure out what this x value is and what this x value is. Well, I guess that's just where the two equations are equal to each other. So let's first set those equations equal to each other. Again, if you have a calculator, you can do all of this on your calculator. But we're just going to do this by hand because, you know, that's so much more fun. A little factoring should do it. X equals 3, x equals -1. And that looks like my picture. That's accurate to my picture, so I think I did my factoring correctly. So I'm going to find the area between these two curves from -1 to 3. Of course, to use our handy-dandy little equation we came up with, we have to figure out what equations, what functions on the top and what's on the bottom. I can see that easily from my sketch here. So we're just going to set that up. The integral from -1 to 3 of my top function, which is 2x plus 5, minus my bottom function, which is x squared plus 2, all with respect to dx. And that is the area enclosed by those two curves. Okay? Don't forget to distribute that negative. Don't forget to integrate. And again, if you have a calculator, you can do this by hand. I'm sorry, you don't have to do this by hand, but we're going to do it by hand because it's more fun. So let's see, oh my gosh, I'm running out of room. So this is going to be 2x plus 3. Let's just do that with respect to x. That's going to give me x squared is the antiderivative of 2x plus 3x minus 1/3 x to the third, evaluated from -1 to 3. And you can do all of that arithmetic. And drum roll, please. Our answer is 32/3. Okay. So now, of course, these aren't always that straightforward. Let's try this one right here. So find the area enclosed by sine of x and cosine of x over the interval. Okay, so now I'm giving you the interval, so we don't have to worry about setting them equal to each other, or do we? So sine of x, I know what that looks like. So I'm not going all the way to 2 pi, so I'm just going to do half of its cycle. So there's my f of x, there's my sine of x. Cosine of x, let's see, that starts at its maximum at 0. And so that's going to look something like that. That's kind of kooky. And I've been told I'm going from 0 to pi. So 0 to pi. Ooh, do you see what I see? I see that there are some times when the cosine function is the top function and the sine the bottom, and another time when the sine is the top function and the cosine is the bottom function. So we're going to have to set up 2 integrals, okay? So we do have to figure out when this transition piece happens. So let's think about this. When are cosine of x and sine of x equal to each other? That's right, 45 degrees, or in radian land, pi over 4. All right, so I'm going for my first integral. The area enclosed by these 2 curves will be from 0 to pi over 4 of my top function, which is cosine of x, minus my bottom function, which is sine of x dx, plus this piece right here, which is going from pi over 4 all the way up to pi. My top function is now sine of x, And my bottom function is cosine of x dx. Okay? So there's your integral. And again, we could do this by hand, but I'm not going to do that right now. If you do this by hand, the answer you get should be 2 times the square root of 2. Okay, pretty fun.